current, and resistance. Electric current. Electric current is a rate, and it's the average current is just the change in charge. In other words, the amount of charge that goes by a point per unit time. Now, if you're using calculus, like the AP Physics C kids must, then you've got to look at it as an instantaneous rate of dq dt.
Delta.
Q is the amount of charge that goes by a point in delta t. dq is the infinitesimal amount of charge that goes past a point in the infinitesimal time dt. Now, important concept is conventional current. What you got to understand is that you could have current if you have moving positive charges or moving negative charges. Now, if you have 1 coulomb of charge that goes by a point in your wire, that's the point, some point in your wire, doesn't matter where. If you have that amount of charge go by in 1 second, 1 coulomb per second is called an ampere. 1A for ampere is the symbol for that. I'll put that down here. That is 1A is the symbol for ampere. That means 1 coulomb per second past a point. Notice that these positive charges that I'm pretending are moving from high potential to low potential over here. Now, if you had 2 coulombs go by a point in 0.5 seconds, 2 coulombs, 1, 2, in 0.5 seconds, the current in that situation, the average current will be 2 coulombs divided by 0.5 seconds. That gives you 4 amperes. Now, the interesting thing is that you've got to count charges that are moving, positive charges moving this way are counted the same as negative charges moving this way. So if you've got each of these little positive charges, 1 coulomb, 2 coulombs, going past that point, also you have negative charges, each one of those represent a coulomb, going past this point that way, the average current, that is 4 coulombs of charge going by in 0.5 seconds, that is 8 amperes. We got to count positive charges moving to the right the same as we count negative charges moving to the left. Now, what I'm going to demonstrate now is the concept of conventional current.
So what I have here are some quarters, which are going to represent the nuclei of atoms, and some pennies, which represent the outer orbital electrons in the conduction band. And if I turn on an electric field, as we'll see, this all makes sense, but if the electric field is pointing this way, the electrons will actually be pulled this way. So let's say I'm turning on the electric field and it's pointing this way from this end, and the electric field moves very quick at the speed of light. It pulls this electron off. Now, first of all, I want you to notice that there is now a positive charge right there. There's a hole there. There's a missing electron. When the electric field gets to here, it pulls this electron off, which goes to there, and then eventually gets to here, pulls that electron off. Then it gets to here, pulls this electron off, and then it gets to here, pulls this electron off. Notice now that the positive charge is right over here. So if we reverse the tape here, started with a positive charge here, and we ended up with a positive charge here. So we can, in fact, say that positive charges move this way. And in fact, in hole flow, in semiconductors, even though it's just a missing electron, quantum mechanically, it is identical to a moving positive charge.
It is the convention to assume that positive charges are moving. For the rest of this year, we are going to pretend, even though we all know better, we're going to pretend that positive charges move. And in fact, if you have an ionic solution, positive charges do move. In NaCl, the sodium ions, they do move one way while the chlorine ions move the other way. So you can have actually positive charges moving.